Hello, Science 30, and welcome to our fourth lesson on bending light. Today we're going to talk about reflection, refraction, diffraction, and polarization of visible light. So prior to this, we have been focusing on things like radiation, so one end of the spectrum. Now we're going to look at visible light, which is in the middle of the spectrum, and talk about the different ways it can be bounced around or moved. So what is visible light? It's a very, very small portion of the EMR spectrum. It's the part we can see and what helps us see color, but essentially it's really, really small. So if you look at your entire spectrum, it doesn't last very long in the world of wavelengths. When we look at visible light, we also see them in colors. So you actually, each different level, so blue, yellow, orange, green, all of those, they have different frequencies and wavelengths. So if we're looking at colors that have the highest frequency and the shortest wavelength, so it means they move really fast and their waves are really close together, we're looking at blues and purples, so blue and violet. On the other end, if we're looking at colors that have the lowest frequency and the longest wavelengths, we're looking at the reds and the oranges. So in visible light, there's even a change in the wavelength in the sense that the colors have different wavelengths and different frequencies. So in order to remember your colors, just Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. So let's talk about visible light and when it is reflected. So we call this reflected light, all right? We see reflected lights of objects all the time. Okay, so like for example, in this picture over here, we can see a light coming in, hitting a mirror and reflecting out. You also notice that the angle that this is coming in is the angle that it reflects away from this mirror at. And we're going to talk about that shortly. Reflected light is when it bounces off of something. So a mirror is a perfect reflector because we can use a mirror to bounce light off and look at reflected objects. So light hits the mirror at an angle and then is reflected, like you can see here. Now, if you have a body of water that's a nice, perfect, glassy body of water, you can also see a reflection in that body of water. So what we're going to look at is when a light comes in and hits a mirror, what are we talking about? This is something you may remember from grade 8. We do talk a little bit about the law of reflection in grade 8. So what we call it is the angle of incidence has to equal the angle of reflection. So when light comes in and hits a mirror, the angle it comes in at is the exact same angle it's going to bounce away from the mirror with. So what does that mean? Incident light hits at an angle, it's reflected at the same angle, and we measure that from the normal or perpendicular from the mirror. So what that is saying, guys, is here's light, it's coming in and hitting the mirror, and it's bouncing away from the mirror. Right where it hits the mirror, we measure and create something called a perpendicular. It's straight, it's a line straight out away from the mirror. Then what we do is we measure the angle from the normal to where the light is, and from the normal to where the reflected ray is. And what that does is that shows that we have the same angle no matter what. Now you may remember refraction. Refraction is another form of bending of light. So the other one, we bounce light off of something and it moves back in the direction it came. In refraction, we're just changing the direction as it moves through different mediums. So if you think about dipping your finger in a glass of water, or perhaps you are in a lake and you look straight down because you dropped something and you want to grab it and you go to reach for it and you can't quite figure out where it is. Refraction is that. EMR waves bend when they move from one medium to another and change speed. So the more dense a material is, the slower it moves and then it refracts. So again, this is called refraction. Let's look at this and talk about what's happening. So when light comes in and it hits this glassy surface, it's bouncing off and that is being reflected. But we're also seeing refraction here. So where the normal is during a reflection, okay, we use that normal when we talk about refraction. So what happens is when light travels from a low refraction index, meaning something like air, which is less dense, and it moves into water, which has a higher index fraction because it's more dense, the light bends towards that normal, that line that we created with reflection. So you can see here it's coming in and it's moving from air to water. Water is more dense, so it bends towards that center line, and that is called refraction. Diffraction of light is really interesting. I think diffraction of light is quite sound waves and any waves or light waves is super cool. So just like when waves bounce off a solid object, so if you shout something like in an area where there's an echo, okay, it will bounce back to you. Okay, so we know that sound waves can bounce off. Okay, but what we also have discovered is that if there's a small gap or opening, if we're shouting at a wall but a window is open, okay, those waves will actually bend around the edges of the opening. So what you're seeing here is light waves coming in and we're trying to bounce it off a wall, but that wall unfortunately has a small hole in it. So rather than the light traveling straight through, it travels and it bends around where that obstacle was, and that's diffraction. So you can see it here a bit better. We have these waves coming in, hitting this wall, but because the wall is an obstacle, but there's a small hole, it creates diffraction on this side. Okay, and we can use diffraction with all different types of wavelengths. Now, interesting enough, an owl uses diffraction. When it hoots, because their whoos or their whoo is a really low frequency, okay, that really low frequency actually diffracts really nicely around trees. The higher the frequency, the harder it is to diffract around larger trees, because remember, it's a smaller wavelength. But if you have a larger wavelength, you can diffract it around. So owls use that to communicate around the forest to each other. When elephants are walking through really dense vegetation, they use a similar method. So they kind of can lose each other in amongst walking through really tall grass, but they use something called infrasonic communication, which essentially means that they are using some sort of diffraction. So when, let's say, they're walking and one elephant at the front turns right, they can send a communication, a diffraction communication, back to the person at the end of the line, so they all move together in the same direction. Diffraction can also be applied to telescopes because we want to use telescopes that have really large openings to allow as much of the starlight to enter as possible. So what we do is this allows scientists to observe fine details, even though diffraction can occur. Okay, so it's really interesting. The larger the lens, the better it is. But we're going to talk a lot more about telescopes later on. All right. Now, there's also something called diffraction gradients or diffraction gratings. Sorry. Okay. And you can kind of see here from the diffraction right here. This is the diffraction grating. And you can see the angle of the light coming in, the reflection that it creates. But then you can see all the orders of diffracted light that come, because when it hits, there is a small opening that allows for it to then grate and show you a variety of different colors. Polarization is one you may be familiar with because you might own polarized lens. A lot of sunglasses have polarized lenses. Okay, most of the times when you see a picture of the electromagnetic spectrum and the magnetic field, that they are running perpendicular to each other. So one is running up and down while the other is running out like left and right. So those are what we're showing here, electric field and magnetic field. But when you have polarization, this is when we take those waves and we confine it to vibrate in one direction only. So you can see from the second diagram, I have the magnetic field and the electric field, and I've shrunk it down to one wavelength. Okay. What this does is we can use filters or polarization lenses to block out light that we don't want to have as it travels in towards our sunglasses. So we are able to filter out light and orientate it the way we want. So we get a more crisp and clear picture. Okay. So we kind of tone down the reflection. We're able to then orientate light to, if it's light waves, into one straight line so we can see things a little bit better. Okay. So again, it stops the light from reflecting into our eyes or a camera lens. So a lot of polarizing lenses are going to be found on cameras, sunglasses. If you're looking at these two pictures, you can see that one, if you're looking straight at the ocean, you can tell there's something on the ground, but you can't really see what. But with a polarized lens, it allows you to see more because we're able to stop the reflection of light. So we're going to quickly watch this video.
Here I'm playing around with polarized light. Sunlight is unpolarized, so it doesn't really matter what angle that if I use a polarizing filter. If you have two filters, and they're polarized in the same direction, then essentially nothing too interesting happens. If the polarizers cross, then essentially light making through one filter is horizontally polarized. Then the next filter only lets through the light that's vertically polarized, so cumulatively nothing makes it through. This is used to have adjustable filters in photography fairly often. Now, something really interesting starts to happen, and in fact a quantum effect begins to kick in if I ask 3 questions. So surprisingly, the answer I get depends on the order that I ask the questions. So if I have a horizontally, diagonally, and then vertically polarized, I get a different answer than if I ask horizontal, vertical, or horizontal, vertical. So in between, I actually get a lot more light transmission than you would expect. And this is an angular dependent sort of transmission. So it has to be between asking the horizontal and asking the vertical question that I ask this diagonal question. And this is really a quantum effect. So if I ask the photons the same questions in a different order, I actually get a different answer, which seems a little disturbing to me.
All right. So ladies and gentlemen, those are the 4 different ways that we move around light. So please make sure you have them in your notes, and I will talk to you soon.